Hello everyone. In this video, I'm going to show you an example for your homework problem. It's problem 7.664. And this is a setup of this problem. So initially, there is a block, okay, at the bottom of the inclined surface, and it's amount on a spring. And initially, the spring is compressed by 10 centimeter, and this block is initially at rest. And after it releases the spring, the block climbing up to the surface. So he asks a problem: will the block reach the top of the inclined surface? And if it's reached to the top, what is its kinetic energy at the top? Okay, top is it means that here. Top means here. Okay, this is top position. This is top POP, the top position, and this inclined surface is not frictionless. It has a friction. It gives you the friction coefficient, kinetic friction coefficient 0.5, and the weight of this block is 4.5 Newton, and the elastic constant or force constant of the spring is 2 kilonewton per meter. It's kilo here, small k, so it means 10 to the power 3. Okay, you have to understand that it's a prefix. And okay, so it's a very typical using a typical energy conservation problem. Okay, so let's first of all let's write down the energy conservation equation is delta K. I should use capital K. Okay, much better. Plus delta U. Capital U is equal to Q plus the work done by the external force. But in this system, in this setup, there is no external force, so there is no work done by external force. We won't have heat. And the heat, like I say in this course, the heat is mostly generated by the friction force, because this is not a frictionless surface, a rough surface. You have friction coefficient. Okay, so for energy conservation problems, so delta K and delta U, we have to do some analysis. We have to do analysis of initial state and final state. Initial state and final state. And okay, I forgot to mention something. The length of this surface, inclined surface, distance of this inclined surface is 2 meter. Okay, so in this problem, I assume that the m move distance d on this rough surface, rough inclined surface d. It's an intermediate state. Okay, I just assume the block move a distance d on the surface. Okay, it's an intermediate state. And I make the initial state, final state here. Initial state, I call this initial state, and the ground and final state is the after the block moving a distance d on the inclined surface. So that's our final state. Okay, why I do that? Why do I have to do that? You will understand. It's very much easier to solve the problem. Okay. Okay, so what's the initial state? Okay, initial state. Okay, what's the initial state kinetic energy? Because at initial state at the bottom, yeah, I say the problem is that the block is at the rest, so there's no velocity. No velocity. That means no kinetic energy. And do we have the spring potential energy? Yes, we have, because initially this block is mounted on the spring, and the spring is compressed by 10 centimeter. So the elastic potential energy 1 over 2 kx squared is just equal to 1 over 2k here. K is 2k, so 2000 and 0.1 square. And I think the answer is 10, right? 10? Yeah, 10. And do we have gravitational potential energy in this problem? Because this motion, it has height change, because from bottom to the top, there will be a height change. So we have to consider gravitational potential energy. But at the initial state, because we can set the height origin at here, it's the height origin here, h equal to 0 there. So at the beginning, the gravitational potential energy also 0. So it's 0. Okay, so what's and we will do the same analysis as the final state. Okay. The final state, I just said the final state is when the block moving a distance d along on the inclined surface. Okay, at the final state, what's its kinetic energy? Because it's at its intermediate state, it's moved up to the surface to a point F, it must carry some velocity, but the velocity I don't know. So I just call it VD squared, okay? And the next one is if we have, do we have elastic potential energy at the final state? Because after release the spring, after release the block, the spring back to its original position, right? The compressor spring first, but after release the spring is back to its original position. So it's back to its equilibrium position. So there's no elastic potential energy. So it's 0. And do we have the gravitational potential energy at the final state? Yes, we have. Be careful. We have potential energy here because here, okay, let's do this. Because the height here is d sine 30 degree. Don't forget it's d sine 30 degree. Okay, this is geometry. Don't forget. So we have the mg is and d times sine 30 degree. That's our potential energy at gravitational potential energy at the final state. So we have all information of kinetic energy and potential energy. And next one we have to deal with is the friction. Okay, and the friction is just the friction. It's a work done by friction. So it's because it's released heat, so it's a minus sign. So we have found the friction times d, and d here, distance d, I don't know. So I call it d. And next one is what is our friction force? Friction force in chapter 5 is nu k, friction coefficient times normal force. And what is the normal force when object placed on the inclined surface? Do you remember that? Okay, so this is still a force analysis. So we can decompose the weight on the end sitting on the surface. So where is, I think this is 30 degrees. 30 degrees here. Okay, since this block moving along the surface, so there is no acceleration perpendicular to the surface direction. So the acceleration perpendicular to the surface direction is 0. Okay, because it's moving along the surface, moving along the inclined surface. It's also 30 degree. In moving along inclined surface, there is no acceleration perpendicular to the surface direction. So, so this Newton's second law give you the 6 net force equal to ma. So but no acceleration, so net force equal to 0. Okay, net force, not net force. Yeah, net force equal to 0. Yeah, because no acceleration. So you will have normal force minus, because this direction is positive and this direction is negative. So be careful for this. It's mg sine theta or mg cosine theta. Be careful. Be careful. It's mg cosine theta. mg times cosine 30 degree and equal to 0. So you have your normal force is mg times cosine 30 degree. And so we have normal force, so we also have friction coefficient, so we can get our friction force. So our heat is equal to minus sine and times nu k times normal force and times the distance, don't forget. Okay, and so we have all the information, okay, for this equation. So let's put everything back into the energy conservation equation and see what happened. Okay, so that's right, let's change to black. Okay, so it's kf minus ki plus uf plus ui, sorry, minus ui equal to q. Okay, so final state kinetic energy, I don't know, so 1 over 2 mvd square. Initial kinetic energy, I mean, remember, is 0. And final state potential energy, To remember the final state, we have the gravitational potential energy, right? So it's mg times d sine theta, sine 30 degree. And initial potential energy, I think it's elastic potential energy, right? So I remember it's 10. Okay, so it's 10. It's 10. And what's our heat? Is a minus 0.5 and mg times cosine 30 degree times d. Okay, so let's put some numbers in there because this problem told us the weight is 4.5 Newton. Okay, so here we see this is 4.5 Newton. This is 4.5 Newton, and what is sine 30 degree? Okay, sine 30 degree. Here is this is 0.5, and what is cosine 30 degree? Let's say it's 0.866. Okay. So the first term, 1 over 2 mvd squared, the kinetic energy, I just don't just preserve it. Don't touch anything about this term. First term, you will understand why. And okay, that's plus. Okay, what's this value? Mg times d times mg is 0.5. Oh, it's okay. It's easy. It's 2.25 d minus 10. And the right hand side is 4.5 times 0.866 and times 0.5. And okay, it's become minus 1.9485d. Okay, you will understand why I have to do this trick. So the first of all, don't change kinetic energy. So it's equal to, okay, let's see, it's 10 minus, okay, plus 2.25. So it's 4.1985 minus 4.1985 d. Okay, this I said this is a kinetic energy when the block move along the inclined move on the distance d on the inclined surface. So I just rename it. It's k. And right now our k kinetic energy is a function of d, and it's 9 minus 4.1985 d. So right now, I make the kinetic energy of block on inclined surface is a function of the distance on the inclined surface. So it become very easy to answer this problem, because at the top, the distance, the d is equal to. So you just put the d equal to, plug into your formula, right? So at the top, so here. So here at the top, d is equal to, so k over 2 is plus or minus 10 minus 4.1985 times 2. Okay, it's still positive. It's still positive. Okay, it's still positive. It's still positive. Okay. Okay, still positive. Okay, I think the answer is 1.6. Okay, it's still positive. That means when this block moves from bottom to the top, it still carry the kinetic energy still there. There's not become to zero. Okay, kinetic energy always larger than zero. Okay, be careful. Okay, so at this top, it still has 1.6 joule kinetic energy. And by this initial setup. Okay, kinetic energy is always greater than zero. Be careful, because kinetic energy, yeah, you know that 1 over 2 mv squared, so k is always greater than zero. Yeah, if you get this equation and you found your kinetic energy less than zero, that means it's dry out the whole friction process, dry out the all kinetic energy. Okay, yeah, this it dissipate all kinetic energy. If you calculate, if the K over D you calculate, if you put some D in there and find it's negative, that means it's the friction dissipate all the kinetic energy. Okay, okay, so negative value here means just zero. Okay, because kinetic energy always greater than zero, so the minimum value of kinetic energy is only zero. Okay, if you calculate this equation and found less than zero values, that means the friction dry out all kinetic energy. But in this problem, yeah, we put a d equal to in there, it's still positive. Okay, that means then the friction did not dry out the friction did not dry out, dissipate all initial kinetic energy. So it still preserves the kinetic energy at the top. Okay, so here's a problem for the 7.47, 7.64. Okay, this is my solution to this problem. Maybe, but actually this problem you can use various way to approach this problem. But here is mine. Okay, I like to, in this problem, I would like to put the kinetic energy is a function of distance along the inclined surface, and it can let me easy to answer any question. Okay, answer any question about this problem. Okay, so here is the video. So see you in next video. Bye bye.